I'd like to introduce Tom Mueller, who's coming to us from the University of Tennessee. It's evening there now, and so good evening to you, Tom. How are you?
Happy to be here. Thank you, Peter. Can everybody see the slides okay?
Yeah, we've got it, Tom. That's fantastic. And yeah, so what's the weather doing in Tennessee at the moment? What season are we in there? Coming into winter, I imagine.
Yeah, we've had a couple of nice days lately. We've had an extraordinarily wet October, which is very atypical for our geography. But we just planted our winter wheat and canola. We grow canola here as a winter crop in Tennessee. Harvest is about completed and everything. Cotton harvest is 75% complete in the state. So we're entering our fall-winter period. Over
to you, Tom, and it'd be great to hear from you.
Okay, thank you. First off, it's a pleasure to be here, and I'd like to show where I'm from. For those not familiar with our geography, I've got an orange star in the middle of Tennessee. It's been a very turbulent last couple of days. We have a game called football, American football, in the United States, and the college football is really big, and we fired our coach yesterday. So the poor guy, he's only going to get $8 million to not coach anymore. So that's the big news around Knoxville, Tennessee. Besides that, I just want to talk today about, have a brief introduction, talk about my background, just about one slide of that. I want to share some field observations that are shared. My coworker is Dr. Larry Steckel, based in Jackson, Tennessee, and I have the great privilege of working with Dr. Steckel. He's a fantastic scientist, and it's just a pleasure to work with him and all the team. I also then want to get into a few studies. We have about 3 or 4 studies of data we want to share with today, and then just some general specific observations. And if we have time, Peter, we'll get to what happened in the United States in this year with respect to field observations of Dicamba off-target movement. And then just a couple of next steps coming forward. The EPA has made some label changes, so if we've got time to get to that, that's fine. The stated goals that I had was sent to me with respect to the webinar was to talk about the rate and prevalence of volatilization under varied conditions, and to explore what our experience has been this year. Really, we've had 2 years of the seed trait being available, 1 year of legal use of the Dicamba products, and what's going to happen in the future. Views expressed by me do not express the views of the University of Tennessee, the Institute of Agriculture, the Department of Plant Sciences, the Department of Agriculture. My primary funding source is the Tennessee Soybean Promotion Board, and mention a product does not mean that there's not other products that'll do just as good a job. I just want to say that this is kind of unique because all of this data is not published. It's all preliminary and subject to interpretation. So many of the times we kind of withhold data until we actually have it published in referee journal articles. And on this particular matter, given the pronounced interest in this data, I've decided to present it in situations like this and to other scientists just to get it out there and they can use it for their informative purposes. I was born on a small farm in southern Illinois. I have my bachelor's in Illinois, my master's from Kentucky, my PhD from Georgia, and a postdoc in Mississippi. So I've traveled around Tennessee. I've been here since 1991, and I work in environmental fate. And my actual proper training, if I can use that phrase, is I'm a weed scientist. But I do have quite a bit of chemistry background in what I do. If you think back a year ago in Tennessee, the major issue we were dealing with was glyphosate resistance. I mean, that was the focus area. And that's really what is driving all the tremendous interest in the Xtend platform, because we were having broad acre agricultural situations where we were having complete weed control failures. And that was really a great concern. So we knew that we needed alternative technologies to improve weed control. From a national perspective, the greatest weed of issue is palmer amaranth in the south. But from an acreage standpoint, water hemp in soybeans is really a much broader acreage area up in the Midwest. So, Peter, I just want to make sure everything's going okay. Peter, can you still hear me okay?
Yeah, everything's just fine, Tom. Yeah, coming through loud and clear. So, yeah, keep on going.
All right.
We'll pause for questions in a minute. Yeah.
Okay, just let me know. So if we started into early 2017, we first feared, and the first reports was that we had non-target site resistance. NTSR is non-target site resistance. And our initial field report showed incomplete palmer control. I was at a meeting, actually a weed resistance meeting in Denver, Colorado, and Dr. Steckel sent me this picture. Now this picture here is a palmer pigweed after application after a correctly applied full rate of Ingenia or Dicamba. Ingenia is the trade name for the BAPMA salt. It's a BASF product. And so when we first started seeing this, you can see up in the top of the image, there's some ones that had very good activity and some had a middle activity, but others were largely unaffected. So to say that we were concerned with resistance the first year of use was a tremendous understatement. So we were very concerned. Now the good news is a sequential application ended up with excellent control. So that was just the way that story played out. So our first fear was glyphosate resistance, and we were using, and then did we have non-target site of the dicamba right out of the box? So that was kind of a scare, but as it turned out, it was not founded. Our later observations showed that the sequential applications provide good control, and this is what probably most farmers are actually going to be doing. If they have any appreciable broadleaf weed pressure, they're going to have a planned pre-emergent application followed by an early post and then a sequential like 14 days later. And if you have any appreciable populations at all, that's what most farmers are going to do from a weed control standpoint. Now, as we got into later in the season, so in our situation, this was going to be, we plant mid-April, early May, and then we're going into harvest in September and October. So it's obviously the inverse of your season. We were starting to see dicamba injury to soybeans widespread throughout the soybean producing regions of Tennessee. And so this is a picture from Dr. Steckel again, and the dicamba symptoms are uniform over the entire field with no apparent drift pattern. And I would say that most of the people listening to this webinar are pretty familiar with a classical particle drift type of drift pattern where it has a more or less designated source. The wind is blowing from one direction and the symptoms are in a gradient. So right next to the treated field of the source of the drift, it has more plant effect. And then the farther you get away from the source, the less pronounced are the injury symptoms. Well, what was immediately striking on all these fields is that's not the pattern. And you would have, I mean, this field is probably maybe 150 hectares. And so there's no discernible pattern. This type of distinctive symptomology is over the entire field. And it's for those who have not been familiar with dicamba, which may be some of you, dicamba causes a very distinctive plant response where it has this upward cupping of sensitive vegetation. And unfortunately or fortunately, this symptomology is uniform. If it's an oak tree or a rose bush or a tomato plant, or in this case, a soybean plant, it has a very characteristic upward cupping of the affected vegetation. So as we got into what this meant was our concern shifted from weed resistance, which turned out to not be the greatest concern, to non-target movement of dicamba. Peter, you want to see if we want to pause and see if there's any questions right there?
No questions yet, Tom, but well, there is one from me. I just wanted to clarify, when you're applying dicamba sequentially, is it about 14 days apart?
Yeah, it's usually 10 to 14 days apart. That's kind of a target. It might be a little bit different than that because at that time of the year, we're having sporadic rain showers, so you may not be able to get into the field as quickly as you would like, but that's an approximate time interval.
And so that first failure was confirmed as not resistant, but it was just that really to kill pigweed with dicamba, you need 2 sequential applications.
Yes, and there may be some isolated instances where there are resistance, but that hasn't been widespread.
Okay, no, all good, Tom. There's no questions coming in yet. Oh, there is one. Are the symptoms of dicamba different from 2,4-D? One person has asked.
Yeah, the question, okay, Peter, let's get the rules down. Should I repeat the question or not?
No, that's okay, though
Okay.
everyone would have heard that.
Okay. Yes and no, they're both auxin type products, but you can tell the difference between 2,4-D, which is going to be more strapping, more epinasty, where the dicamba is going to cause a more distinctive upward cupping. I'm going to go, it's going to be, so if this was a 2,4-D, you would see more epinasty in the top of the leaf, and you would not see this very distinctive upward cupping. So, but that being said, at very high rates, like if you have a direct application or a missed application, they do look more similar because they just totally mess up the and have undifferentiated plant growth.
Yeah. So yeah, 2,4-D is more twisting and dicamba is more cupping, is what you're saying.
Yeah, I would say that's true.
Yeah. Okay. Yeah. Keep on going, Tom, and we'll pause for questions again when there's a few through.
Okay. Just want to say that this is not a new research area for me. This is studies that I did in conjunction with Monsanto, and the field studies were actually done in 2009 and 2010. And this is a Weed Science publication that was co-authored by 2 Monsanto researchers. And so I've been doing research in this area since that time. So I'm going to show studies, 3 field studies, and this is all field studies, about our data for today. And the first study is the effective surface condition, which means is it bare ground, is it green live vegetation, what does that effect does that have on the dicamba volatility? The second study is the effective dicamba formulation, where I'm examining Xtendimax directly to clarity, which is a diglycolamine. And the third is looking at the effect of mixtures on dicamba volatility. And on this particular study, I'm only showing Xtendimax, or excuse me, Angenia, a dicamba formulation plus Roundup. So let's go to talk about this. So the first question is, how does surface condition affect the dicamba volatility? So I set up these plots prior to application, and we had three basic types of condition. We had tilled ground, where we removed all vegetation and it was actually loose dry soil. We had a no-till situation where we had dead plant vegetation, which had been killed completely with paraquat. And then we had the third surface condition, which was live green plant vegetation that was approximately 10 centimeters high. So we used, I sprayed Clarity, which is a middle of the, it's not, there's 3 basic types of dicamba formulations. There's the Banville dimethylamine, which is highly volatile. There's the Clarity, which is reduced volatility. And then there's the new formulations, which have supposedly or ostensibly lower volatility, and that would be Xtendimax and Angenia. So Clarity is probably going to be used in a burn down situation in a pre-emergence because it costs a lot less. And I did a higher rate because I didn't know what kind of signal I was going to have. Now I collected discrete samples at 4 sampling intervals. So I'll show you this on a slide in a minute. Now I want to be real clear about this. The samplers are not outside the treated plot. They are inside the treated plot because I didn't know how much I was going to have coming up from the soil surface. The other observation is that there is a viewpoint that once you have any rainfall, all volatility stops. And this data addresses that because in the middle of the study, we had a rainfall approximately 12 hours. HAT is hours after treatment. So looking at the data.
Just quickly for those of us on the metric system, Tom, that pound per acre is, I think it's roughly 1,100 grams per hectare.
Yeah, that is correct. So I would say it's a 2x rate of the normal dicamba rate. Does that speak to your question, Peter?
Yeah, that's right. Okay. I just sort of put it in context for everyone in Australia here.
Sure, no problem, no worries. So this is the data from this first study. It was in Knoxville from the June of this year. We have the green bars represent dicamba emitting from green plants that are what's being sprayed. The orange color is from dead plants, and the light blue is from tilled soil. The first sampling interval is from 0 to 6 hours after application. So it's sprayed first thing in the morning. So this is the morning of the application. 6 to 12 is the afternoon until basically at dark. So this is the afternoon of the first day. 12 to 24 is overnight. 12 to 24, so this is the overnight sampling period, and this is 24 to 36. So this is from sun up to sunset the next day. And so it's the same series for all 3 surface conditions. So the green plants, I'm spraying green plants and then measuring the dicamba volatility. Now, you can express this data in a wide variety of ways. And so after having lots of parts per billions and things like that, what I decided to do for this type of demonstration is dicamba nanograms per hour, because that way you get a sense for how many you got an hour unit here in nanograms. And so the bigger the bar, the more dicamba that is coming off of that plot. Okay, so looking at the 3 types of surface conditions, what you're spraying appears to have a pretty substantial effect, because if I'm spraying green plants, I'm getting a lot more dicamba as compared to dead plants or tilled soil. So that's the first thing that comes out, and it's a pretty substantial difference. It's about 10 times as much. The second aspect is the time interval, where the first morning I'm having, you know, a substantial amount of dicamba coming off, but in the afternoon, that's when you have the largest flush, or the largest amount of dicamba being detected. When it comes to overnight, it goes down, and then you have some the next day. And I've done about 7 or 8 of these studies over the years, not this particular with the surface condition, but I see this pattern where I have some the first morning, more in the afternoon, decreased at night, and detected the next day.
So there's a question come in, Tom, someone asking what was the temperature over this period, and is the volatility related to temperature?
The answer is that's a very good question, and the temperature, it was 72 degrees, so that's about, what is that going to be, 14 C maybe? So this was early in the season, so it's pretty cool. It wasn't very hot, and I've got temperature data in the later study, so we'll talk about that. But in answer to his question, the temperature is going to have a major effect on the volatilization. In fact, I've got a lot more data than I'm talking about tonight, but I think that's going to be the actual key driver. And if you look backwards 20 years ago on previous dicamba used in the United States, they had a temperature of 85 degrees was a trigger temperature that was really a factor in this use. Does that speak to that question?
Yeah, I'm just trying to Google that conversion. I'm not very good at doing Fahrenheit to Celsius, but I'll.
Yeah, but I would say it really wasn't very warm, and the other thing is, at the end of this sampling interval, it rained. See right here, rainfall occurred at 12 hours after treatment. So it rained, so it really reduced the temperature then, so it wasn't very hot at all for the next day. So 2 things. First off, even though it rained at the end of this sampling interval, there was still measurable dicamba, especially from the plant material. And so we've got, you know, half an inch would be about 10 millimeters of rain. So it was a pretty, you know, not like a huge rain, but enough that it could have incorporated the dicamba into the soil, and still we had detectable dicamba even after the rain. So, yeah. So anyway,
so the answer was it's 23 degrees. Thank you, Claudio, for 23 degrees Celsius is 72 Fahrenheit. And there's other questions coming in about what is the vapor pressure of dicamba compared to 2,4-D and the different formulations, and we'll get to that a bit later on, won't we, Tom? So we'll just pause on the answering of that question for now, Bill.
Okay. Do you want me to go to the next slide, or do you want me to hang here?
You keep going, Tom, and there's a couple of questions there about our formulation of dicamba that you're using compared to the ones in Australia, but I think we're going to get there in a little while. Okay.
Okay, the second study does Xtendimax, which Xtendimax is the Monsanto formulation, and so Clarity is a dicamba formulation that has a diglycolamine salt. Xtendimax is the same formulation with a different components added to it. So Xtendimax is just Clarity plus what Monsanto calls Vapor Grip. And I mean, it's a proprietary blend of something, so no one really knows what Vapor Grip, maybe you Australians know, but nobody in America really knows what it is. And so we don't know what is in Xtendimax that makes it with the vapor grip, and that's what they decided to do. So that's them. The second study had pretty good plot sizes. We were having it was bordered with Roundup Ready soybeans, just non-dicamba tolerant soybeans, and they showed no damage, so that we didn't expect any physical drift. And even though it's not on the slide, it's very common to have all our treatments include Roundup Power Max, because you want to get all the other weeds that are there. And so these treatments also included Roundup Power Max, and the dicamba use rate is 1/2 pound, which is going to be 560 grams per hectare. So 560 grams per hectare, which is kind of working out to be the standard rate. So looking the same setup, this is field volatility of dicamba. This was actually done before the other one. So this is the 0 to 6 time frame, the same time frames. We have clarity, and this is Xtendimax. And I want to remind the listeners that this, even though it's not listed, both of these have Roundup in the tank with them. And we see a very similar pattern where you always have detections of dicamba at every sampling interval. And in this study, the Xtendimax had lower volatility compared to the clarity. So if you look at this bar compared to this bar, it's about a 50% reduction. If you look at the clarity bar and compare it to the Xtendimax, it's a substantial, like a 60% reduction. And then same thing, the same pattern holds throughout the sampling interval. So that's what I mean. Based on this data, the Xtendimax does have a lower volatility than clarity, and the other dicamba that is has been used historically is the dimethylamine or Banville. And if we were to have that same study in here, rather than the line out to here, it would be way off the screen. It's going to be a lot higher bar, and so we don't even use Banville because we know that's going to cause volatility issues.
And I'm pretty sure that's what we use, Tom. I know we definitely use Banville, and I know that one of our other dicambas, which is called Cadence, is a sodium salt. And so I'm guessing that the dicambas that we are using in Australia are a lot more volatile than the ones you have on the screen there. Would I be right?
That would be correct, yeah. Yeah, if yours would probably have bars, rather than 1,000, it might say 2,000 or 3,000 at this top interval right here.
Mm-hmm.
Now that would just, I mean, that's just a supposition because we don't know. But this, we had previous work where the Banville in the paper I showed early, it had much higher volatility compared to the others.
Okay, thanks, Tom. And look, we've got some people out there with a lot of knowledge on this topic. So if you want to make a statement rather than a question, just put a statement in that questions box, and I'll read it out, and it'd be good to have some good discussion.
You want to hold here or go on?
No, you keep on going, Tom, and then we'll pause again in a minute. The only other question was why do you think the volatility was worse on the green plants rather than dead plants or tilled soil? What's driving that?
Well, the truth of the answer is we're doing some more studies to look into that. The evapotranspiration coming from soil or dead plants compared to live plants is a factor. It could be a surface to volume ratio thing because all those leaf surfaces could be a factor. So it's probably not so much a temperature effect because the temperature should be similar between the two. So the actual truthful answer is we don't know, but there's several possibilities. Would be just a surface area and how the molecule is going in. If it's going into a green plant material, and how that's able to desorb back up is just very different than if it hits a soil particle. There is a school of thought that says if it hits a soil, it's going to be kind of adsorbed onto the soil and not allowed to come back up as quickly, because the waxy cuticle of a plant surface may be holding it up and more available for volatility. But the truthful answer is, we're showing what's happening, and we've got some work to do on why it's happening. That's not a very concise answer, but that's the answer we're going to have right now. It's a very good question.
That's okay. Yeah, thanks, Tom. Yeah, keep on going, and we'll get to some more answers about the relative volatilities between different products as we go.
Okay, so based on those previous studies, I we changed a few things around, and we established what I'm going to call, this is probably what we're going to go forward with as our optimized methods. And so we're trying to use farmer scale equipments, which are 10-meter booms. We have TTI, which is turbo T injected nozzle, so it's ultra coarse nozzle, and all the Dicamba labels are going to say you got to use an ultra coarse or super, you know, a very, you cannot have a lot of fines in your applications. Our plot size is about an acre, which is whatever, it's 200 feet by 200 feet, so it's pretty large plot size for us. I have some images of the high volume air samplers that we used. Now, the air sampler height, whenever you're doing modeling work, where you are above the soil surface is really critical. And so I decided to have it about 10 centimeters above the soil surface. And the reason for that is if you put them, you know, 3 meters up in the air, you get a bunch of non-detects and you get a bunch of zeros, which is not very informative. And if you put it too close to the ground, well, you know, it's really, you know, not necessarily measuring the volatility. You may be getting particles coming up and stuff like that. So that's kind of why we picked this particular 10 centimeter height. The sampling interval, we are comfortable with that still. It's the same four sampling intervals. And the reason I get several questions all the time when I speak about this is, why do you only go to 36 hours? Well, the only way I know to make it rain in Knoxville, Tennessee is to run these studies. And unfortunately, these samplers are not waterproof. So we're always watching the weather to try to get in a 2-day window when we could set everything up and spray the study and everything. So future studies, we're going to try to go out farther than 36 hours. But for this data that I'm talking about, the sampling is the 0 to 6, and it's really just the morning of the application, the afternoon of the application. We run the samplers overnight, and then we run them all the next day, and then we terminate the study at the end of the next day. In this particular study I'm talking about, this is going to be Ingenia. So Ingenia is the BASF low volatility formulation, and it has a different mechanism. It has a different salt, and so it's going to be, it's called a BATMA salt, which has lower volatility because of the type of salt that it's put in with it. And it's going to be at a 560 gram rate. And then the two treatments are the Ingenia by itself and then added with the Roundup Power Max. The reason I did the study was the soybean board essentially wanted this exact question answered, because they were having all these problems and there was mixed results. That some people are saying if you put the Roundup in the tank, it really increases the volatility. And I'm going, well, I think I know the answer, but really don't know. And then we had it on treated control. So this is why this study was done, because it was at the direct request of the soybean group. So the applications were made first thing in the morning, and in our geography at 6 o'clock in the morning, there's a very still wind, and you're just really coming out of an inversion, if you want to use that terminology. For this particular study, the surface condition was very small soybean plants, and it was residue, long-term no-till, but it really didn't have a lot of plant material. I mean, I'll show you some slides here in a minute that it's probably 80% going to be open soil. A common question I got when I talk about this is, what's the soil texture? So it's a pH of 6.2 and organic matter of 1.3, so this is a medium texture silt loam soil. And on this particular study, there's no rainfall occurred during the sampling period. So just to show our viewers what we're doing, we tried to get it as close to a farmer scale as possible. Now, in reality, our broadacre farmers are spraying with great big equipment with, 30 or 40 meter booms. So, but this is at least sprayed with a tractor spray with a TTI nozzle. And one of the issues that since I've got a tractor, I'll just show you this. The label says this distance from the nozzle to the application can only be 2 feet. So that's going to be whatever 2 feet is. But so this is, I mean, technically, this is probably 2.5 feet. So this is an off-label recommendation, even though it's not very high. And that's one issue that some people are concerned about, that you've got to keep your boom really low. And I would say the Australians are way ahead of everybody as far as particle drift and how to understand that. So you've got some of the best researchers in the world working on that subject. So I probably don't have to reinforce that. So the samplers, in order to have a high flow rate sampler, the other people who do these, they use batteries all the time. And so if you look at a lot of studies, they only sample for like 6 hours or 8 hours at a time. Well, that's because the batteries give out. And so I decided that we're going to go with generators and 110 volts. So we have a lot of generators, and we run the samplers based on our normal power. We bought the samplers from this company in California, and they have 2 sampling media, a filter paper, and then a puff or polyurethane foam is inside the collector. So this is a field shot. So this has a filter paper. It's really more than a filter paper. It's like a real thick microfiber mesh. So this is what we call the filter paper. In this section here is a polyurethane foam plug, and we're drawing this at a pretty aggressive flow rate of about 6.5 cubic feet per minute, which is a pretty aggressive flow. And so just from an operational consideration, we always have a vent to vent the exhaust gas away from the sampling port, because in a real still air situation, you don't want to have any kind of Venturi effect that you're setting up. But if this is a field study, you can see this is not a lot of vegetation. And so when I say at the end, while we tended to have lower volatility, this kind of goes that there really wasn't a lot of plant material that was being sprayed. So our sampling media, you've got your filter paper and your polyurethane sampling media is assembled into a filter media holder. The application is made, and then if there's anything that is volatilized, it's captured in the filter media, and then we analyze it later. So the field site had 4 samplers in the middle of a larger sprayed area. So we want to try to minimize border effects, and so that's one of the reasons why we feel more comfortable with the bigger plot size. The question was asked earlier about temperatures and so forth, and the previous studies that showed that temperature is a very important factor. So we have so we have these, what they call them, hobo soil temperatures. So this unit measures temperature and relative humidity at whatever time interval you say. So we set these up, and so we have lots of these that we use all the time. Sample collection, they're very difficult studies to do because it's very easy to get contamination. So we go through lots and lots and lots of gloves. This particular image happens to be of the first studies we did with the Monsanto cooperators. So, but it's very easy to get a little bit of a contamination onto this filter media. So it's important to have very good standard operating procedures, to have good sanitation and so forth to avoid contamination. I'm fortunate in that I actually do all the analysis. So when we do a field study, we just take the filter papers, put them in a freezer until we get the whole study done. We extract them with methanol, and we assay them with LCMS. And so that's the people who are all working in this area pretty much are using the same extraction procedures and all that. And I'm fortunate because I've got my own lab analysis that I can run all those in. So going to the data, so 72 degrees was what again? 20?
23.
So this is starting at about 70 degrees. And so what this is, we have weather stations that report air temperature at about 1.3 meters. So that's the standard height for the temperature. So most of the data when we were doing this previously, we would have air temp, and that's what it looked like. Well, but when you actually put a temperature probe right on the soil surface, there's a substantial difference between the soil temperature and the air temperature. And as you go into the heat of the day, that's going to be a big difference, and that is a major consideration in how you do the studies. So this is first thing in the morning. This is about at noontime. This is the heat of the afternoon, and the sun goes down about here. And so all night the temperature goes down. And there's no solar incident radiation, so the temperature is the same, and it starts the same thing the next day. But one of the things that I think we're really appreciating is that the soil temperature and the air temperature can be very much different. And we've done later studies where this temperature is up to 130 degrees. So it's 50 degrees Celsius in the soil temp. And so when you're saying, well, something's not volatile, well, you have some pretty high temperatures that can drive the volatility. So looking at the Dicamba data, this is Xtendimax, which is the Biesa formulation plus around the Power Max, same time course, and without the Power Max. there's a slight differentiation of the different time course, but the average is it's the same. So in this particular study, there was no effect of adding the round of power max to the volatility. Now that's not going to say that that's the same effect that happens every time, because if I have a huge amount of plant material and the surfactant that's in this glyphosate formulation may impact how fast all the herbicides are getting in. So, but all I can say is on this particular study, there was no effect of adding the round of power max to the dicamba product with respect to secondary loss, because all these bars, if you add them up, they're all about the same. But that being said, there was still overnight or the next day, there was still appreciable dicamba being detected. And so that's, you know, the data is what the data is, so that's what we saw. So in general, all the samples we had detected concentrations of dicamba. That's not the result that I wanted to get from this. I was hoping to have a bunch of non-detects, but the truth is we're seeing dicamba after application. In this study, there was no apparent effect of adding power max to the dicamba. As is the case with virtually all our studies, most dicamba loss to the atmosphere per hour was in the first afternoon after spraying. So as it heats up in the first of the day with the largest amount of herbicide concentration there, that's when you see the greatest fluxes into the air. Now, on this particular study, a couple of specific observations. The surface condition was largely soil, so based on our previous observations, that may have had less volatilization. I did mention that the temperature of the soil surface was greater than the ambient air, and when you do the mathematical calculations as how much I collected, the total losses that I'm measuring as a percent of applied were still very small. I mean, almost minuscule. And so when I did the math on these, I was really kind of concerned, because I'm saying, how can this such a small amount be causing all the injury that we're seeing? Well, the reality is the soybeans are an especially sensitive crop. And so that's one of the main issues we're having. And so a very small amount will cause damage. So did you want to stop?
Yeah, that was I mean, after we met the other day, Tom, and you showed me your slides, that was the thing that really hit home to me, is it's a tiny bit of loss, 0.001% of the herbicide is vapor drifting, and that is enough to cause the damage. That really blew me away. More of a comment than anything else.
Sure. Do you have any questions? Or you want to go ahead and go on?
The one question that came in: has there been any research done with other glyphosate salts, or have you just done that one bit of research with Roundup Power Max, I think it was?
No, we don't have anything we can publish yet on that. I do believe that you'll see that the different glyphosate formulations and the pH effect they have on the solutions will have an effect, but I don't have anything else I can share today. But in answer to the question, I believe there's going to be some effect of different glyphosates, yes.
Mm-hmm.
So the general comments, whenever you're trying to do dicamba volatility studies, it can be complicated because it's an interaction of multiple factors. And I think the good questions we've got from the listeners is an indication of that. Is the temperature? Is it surface condition? What's the effect of adding other things into the tank? The other aspect that I think I'm struggling with is the effective experiment scale. So when you're trying to do an acre plot or a 10-acre plot or a 100-acre plot, those are all going to matter as far as your potential outcomes because of the border effects that you do or do not have. So everything I've tried to do is to consider it to be relative. So in that study, what is the relative amount of volatilization? So that's kind of the way I'm looking at it. And the scale of the study, what I'm talking about, when you go from small plots, and I've got a 30 meter by 30 meter, that's in small plot research, that's pretty good size. But when you go to treating 100,000 acres or 50,000 hectares in a county, that's a lot different than treating a small amount in a 40. And so all the research is done, you're spraying 1 acre in 10 or something like that and seeing where it's going. But the reality is everybody's weeds are going to be at the size to spray at the same time. So everybody in a district or in a county, they're all going to spray at the same time. And so even though this really small amount is volatilizing, it is potential that that's going to come up and cause problems. Okay, you want to go to the Dicamba 240?
Yes, please, Tom. And yeah, it'd be good if we could pause
Okay,
here
now
for a
the
moment,
first,
because for Australia, we really are trying to. It's obviously very interesting to learn about what's happened in the US, but our main, I mean, we do use Dicamba, but our main phenoxy herbicide in summer for a fair bit of the country is a 2,4-D formulation. So yeah, it'd be good to compare those relative volatilities.
well, the first thing that is, you've got to add caution, and these are from the WSSA herbicide handbook numbers, and so the methods differ in how they get the numbers, and so you really can only kind of speak in general terms, okay? So because the temperatures are different, and unfortunately, how these numbers are derived are subject to error, okay? But I think it's safe to say, so if you've got acid, you got a -7 and -5. So dicamba is more volatile than the acid. And when I looked up the dimethylamine, it just says they didn't have a number. And this is the ethyl hexyl ester. It's an order of magnitude less than dicamba. So in the take-home messages, most 2,4-D is expected to be somewhat less volatile than dicamba. And that's about all I could say based on the vapor pressure at this time. The other thing is, there's a wide diversity of viewpoints on vapor pressures. And there's some people who say, well, it's going to be the dominant controller and the intrinsic volatility of the molecule will or will not, it'll be volatile, it doesn't matter. And there's other people that say, no, there's a lot of other factors that are going into it. So, if in other studies, which I didn't show here today, I think you're going to have less trouble with the amine 2,4-D volatilities than the dicamba. You're going to have a lot less, I would predict. But that's just, you know, a prediction based on preliminary data. And
so that dicamba that you're quoting there,
that's the acid.
That's the acid. Okay.
Yeah. Because all the others, there's no published vapor pressure for Xtendimax or the Ingenia, because I can't find where they published those numbers.
So given that we are used to using a more volatile dicamba in Australia than you've used in your research, you could say that that for our relative volatility, that the dicamba that we're used to is a whole lot more volatile than our 2,4-D amines or esters.
Yes, and is that what you're seeing? I mean, out in the field, is that what you're seeing?
Well, we don't. I mean, people can come in and comment. We probably see more spray drift than vapor drift in Australia, but we perhaps vapor drift is a bigger concern for the future. I don't know. Other people can comment, but I personally haven't seen much vapor drift at all in my time, and other people can comment. I'm sure it happens from time to time, but spray drift is certainly more common. And so I would say that because we are mostly using low volatile esters or amine formulations of 2,4-D, that we are actually minimizing our vapor drift.
Yeah, and if you have very strong winds that rapidly blow for all the time, well then the vapor is going to be blown away and diluted off target anyway. So that's the atmospheric conditions in much of the United States is you spray it and you have very calm conditions overnight, and it's that overnight movement potentially, or the next day when it's real calm, if the wind's blowing 5 or 10 or 15 kilometers an hour, it just all gets blown away, and we really don't see those being an issue. So
yes,
I didn't go ahead.
Oh, you're right, and other people are commenting that it's spray drift, not vapor drift, is our greatest enemy in Australia, and I would certainly agree with that. But I guess we, in terms of this webinar, we're just interested to stay on the right track, I guess, with vapor drift, and also probably understand dicamba. And one of the things I've truly learnt today is that the dicamba that we're using in Australia is a lot more volatile than what you've used in the US, and you've had a lot of damage in the US. So perhaps I went into this thinking that we're going to learn a fair bit about 2,4-D, but probably what I have learned, and others can comment, is that the dicamba formulation that we're using is very volatile, and perhaps we do have some risk of damage from dicamba in the future.
Yeah, it's quite possible. So, in conclusion on the data part of it, I mean, just want to say that really appreciate the funding from the Soybean Promotion Board. You talked about your funders on the front end. Well, this work was largely funded by our local promotion board. I had several excellent technical assistants from my technicians, and so you know, that's what we want to do. What time we got? 7 to 6:20, 8:20.
So, yeah, we do have 10 minutes for questions. If
you want to just go to questions and then knock it off, is that okay?
Yeah, well, we can do a little bit more if you like, Tom, but I'll just really open it up for questions. And most of the questions, and I do have a few in front of me here, it's all around volatility of 2,4-D versus dicamba and field situations. So there's questions of, for example, if some formulations of 2,4-D are taken up by the plant faster than others, does this affect the amount that's left to volatilize? I'm not sure if I've got that question quite right there.
I understand the question. I don't have a good answer for it because all the 2,4-D work I've done has been on wheat stubble. So I haven't had any green vegetation present at the time. So I can't comment on that. You would anticipate that it would have an effect. I mean, that would make sense. But what the exact effect would be, I would not want to comment because I really don't know.
Yeah. Other people are coming in and saying that vapor drift is a major issue in South Australia, particularly in the Clare and Barossa valleys where we have a lot of vineyards.
Yeah.
And the riverland where, you know, there's a lot of intensive horticulture and so on.
Yep.
So yeah, so 2,4-D vapor drift is probably the biggest issue for us, is where we have those sensitive high value crops.
And so the United States, different states have registries where if you have a sensitive crop, you put it on a website, you register your crop, and then it discourages and is a mechanism that you can go see where are the sensitive crops near you. And we are struggling with, I showed the soybean slides here today, but we have many instances where there's grapes, there's trees, there's the same issues in sensitive geographies are a very, very major concern. So I think the people have a valid concern to be concerned about that.
Yeah. Another one here, our dicamba is rated for vapor pressure. I think the measure is at 1.6 MPa, and our 2,4-D amine is rated at 0.013. So to my mind, that dicamba that we are using is about 100 times more volatile than our 2,4-D amine. But is this still an issue with sensitive crops, especially given that 0.001% of vapor drift of dicamba in the States was enough to damage soybeans? So even though we're using low volatile 2,4-Ds in the most part, is it still a problem because we have such, you know, it only takes a tiny sniff of the herbicide to damage the sensitive crops like cotton in our instance?
Well, that's where I think you want to be careful making generalizations, because cotton damage, cotton damage from dicamba really isn't that substantial, but cotton damage from 2,4-D can be devastating. And I'm sure, some of your listeners have experience with that. So the auxins, the dicambas, and the 2,4-D, the sensitivity to different crops is very different. And so one of the difficult lessons we've learned in the United States is just how extraordinarily sensitive soybeans are to dicamba. And so if your primary auxin is 2,4-D, that may bode well for you that you may not have some of the big problems that we have. But each species is going to have a differential sensitivity. And so in a certain environment, the combination of a certain environmental pattern with a certain herbicide use on especially a large scale can have the possibility of, unexpected movement. At the end of the day, the reason we're spraying stuff is to kill weeds. We're not spraying it out there to not drift, we're spraying stuff to kill weeds. And that's, you know, we kind of remember. And the reason there's so much adoption of this and interest in the United States is because we've got some weeds that are very difficult to control. The glyphosate doesn't work anymore. The PPO inhibitors have stopped working. And so there's a reason why everybody, or a lot of people, have a very strong interest. Now, that being said, what's sad about it, or I don't know what sad the right word is, but because we had so much damage in 17, there are farmers who are buying the Xtend not because they really want the Xtend, they just don't want to get drifted on again. So they're buying it out of insurance or out of defense from their neighbors drifting onto them. Well, that brings up all kinds of issues about, well, you know, that's really kind of restricting your rights, you know, because you're forcing somebody to do something. You see what I'm trying to say?
I do, yeah. And we don't want to, yeah, I mean, it's, I guess, is it fair to say that the drift and the consequences were a whole lot more than anybody expected?
Absolutely. Yeah, I was very surprised. Surprised and disappointed, to be honest with you. I know that in the state of Tennessee and in many other states, they did exceptionally good trainings. That they trained. This is what you need to do. This is how you safely use this technology. I know that the registrants worked diligently to try to get the training out. And so I think by and large, I think most people, including myself, I was surprised by the extent that we had the problems that we had. I mean, I'm running these samples for several years and I'm getting these real small numbers and I'm thinking, well, yes, I'm having positive detections, but, you know, yeah, it's pretty low numbers. And so I think a lot of people were surprised. But, you know, I didn't show some of the slides, but we had about 1.2 million hectares affected in the United States of our soybean acres. So, I mean, this is a pretty substantial amount of affected acres, and that doesn't even count all the vineyards, the orchards, the home situations. So
when you say it like that, it feels like it's a miracle that we've been using these products so long in Australia, Tom, and we haven't had huge consequences. But yeah, I guess there's some consequences, but certainly not as big as you've seen in the States. There's another question here, and it's an interesting one. If we walk into a field 2 days after application and can still smell the product, are we smelling 2,4-D, and therefore there is a potential risk of volatilization, or are we just smelling the solvent in the herbicide?
Well, it's a very interesting question. I applaud whoever wrote that question. That's a good one. Well, first off, the different 2,4-D formulations do have different odor profiles, and so one of the differences of the choline salt, and I don't know, are you using any of the choline salt in Australia yet? The new Dow salt?
I don't know, to be honest.
Yeah, I don't think you are. So one of the differences with the choline salt is it has a much lower, it's called an extinction coefficient. You can't hardly smell it. It has a lot less odor. So I don't know if you're smelling the solvent, which I think you're smelling the active ingredient, because depending on the solvent, that's going to have a solvent smell, which is more like, to use a generic term, it's going to smell like gasoline or, you know, something like that, as opposed to a phenoxy, which has a different type of a smell. And if you're smelling it 2 days later, you know, depending on the formulation, you might have the chance that it could be volatilizing the next day, but it's just going to depend on the weather conditions and so forth. So I think it's a fascinating question, but I mean, I really would be hesitant to answer it specifically. But you're probably smelling the 2,4-D because the solvent smells different from the active ingredient. I think that's safe to say.
Yeah, and we aren't using the choline salt, thanks to those people that have that put that in the question box.
I didn't think you had it yet. So. Yeah.
And so we'll cut it off in a moment, I think, Tom, because we are at the end of our hour. But one last question: if such low amounts of dicamba can affect soybeans, how clean can we get a boom spray that's previously been used for dicamba application? So are we at risk of boom contamination?
The way most applicators have responded to this in the United States, they have a dedicated sprayer that they leave on dicamba, and all that sprayer does is dicamba. And so that's how the commercial people have operated it. Now, that being said, I didn't show any of the data here, but I have an entire research project on tank cleaners. which is very interesting to try to figure out how that stuff. And the truth of the matter is, with respect to getting it out of spray equipment, it's pretty easy to get the Dicamba out, and actually the 2,4-Ds are harder to get out of sprayers than Dicambas. And so the truth of the matter is, if you use any commercial tank cleaner and follow instructions, it's pretty easy to clean the Dicamba out. And I've got the data to show that. So that's the answer on that. Now, that being said, I'm not going to flip back and forth, you know, all the time, but that's what we're going to do.
Yeah, and we have cotton growers here apparently, thanks to one of our listeners who have also dedicated boom sprays for spraying cotton. Well, we're going to wind it up there, Tom. I've learned a lot, and I'd really like to thank you for your time and joining us for the webinar. We love to add an international flavour to our Weed Smart webinars in Australia, and I certainly have learned a lot about the volatilisation of Dicamba and other phenoxy herbicides, and I think it might be a topic we follow up with some more information through Weed Smart, a bit more particular to some of our 2,4-D products. So thank you very much for your time, Tom, and thanks for your presentation, and I hope you can go off and enjoy something to eat now, because it's probably getting late there, is it?
Yes, it is, and it's a pleasure to be here, and good day.